In this video tutorial, we will discuss the topics of solution concentrations and dilutions. When we talk about concentration, we're talking about how much solute is in our solution. Just as there are many ways to express length, like centimeters, meters, kilometers, inches, miles, feet, there are also many ways to express concentration. Now, one such method is by using percentages. There is a percent MV, percent MM, and percent VV. They all have the same general equation, how much solute per quantity of solution times 100%. The only difference is how do you measure the solute and how do you measure the solution. Is it a mass solute per volume of solution, or mass solute per mass solution, or volume of the solute per volume of the solution? Which method I choose depends on what's easiest to measure. Is it easier to measure the mass of a liquid or the volume of a liquid? Is it easier to measure the mass of a solid or the volume of a solid? How about a gas? So if it's easier to measure the mass of a solute, then choose percent MV or percent MM. But if it's easier to measure the volume of a solute, choose percent VV. The same goes for the solution. Is it easier to measure its volume or easier to measure its mass? And that will dictate how we want to express the concentration of our solution. Now, it's very important that you remember solute and the solvent together make up the solution. They all begin with the same three letters, so that can be a little confusing for some students, but make sure you know the difference between all three, because this will become very important when it comes to interpreting these questions. So let's try the first one. If I have 5 milliliters of water added to 4 grams of powdered drug, the final volume becomes 6 milliliters. So what is the concentration of the drug measured in grams per 100 milliliters? As we see from the equation, it's always the solute in the numerator and solution in the denominator. In this case, the powdered drug is our solute, so I'm going to write that in the numerator. My solution volume, is it the 6 milliliters or the 5 milliliters? Remember, solution is made up of the solvent and the solute together. So when I combine 5 milliliters of water, the solvent, what's doing the dissolving, to the 4 grams of powdered drug, the solute, what is being dissolved, this powdered drug caused the water level to rise to a final volume of 6 milliliters. And so the 6 milliliters represents my solution volume. So the ratio of solute to solution is 4 to 6. But it wants it in grams per 100 milliliters. So I need to set up this new ratio and solve for x. And when I do so, I get 66.7 grams per 100 milliliters. The question then asks, what is the percent MV for the solution? So let's plug in these values into the equation up above. Mass of solute, 4 grams. Volume of the solution, 6 milliliters. So 4 divided by 6 times 100% gives me 66.7% MV. So you'll notice the percent MV calculation and the grams per 100 mil calculation gave me the exact same value. So in a way, they are interchangeable. When we use the term percent, the cent represents 100. So century, 100 years. Centennial, 100th anniversary. Well, percent means per 100, which is what we're saying here. So these types of questions aren't particularly difficult. Just take the values, plug them in the equation, and calculate. So please, press pause, try out this question. When you're ready, press play, and we'll take it up. Alright, 18.37 grams of sodium chloride is dissolved in 92.2 grams of water. What is the percent MM of this solution? Since the sodium chloride is being dissolved, this represents our solute, 18.37 grams. Now it's dissolved in 92.2 grams of water. But there's a problem. This isn't the mass of my solution. This is my solvent. Remember, the solution mass is the mass of the solute plus the mass of the solvent together. So I need to add these two values together in my denominator to create the mass of the solution. Things will make, they rush through these seemingly simple calculations, and without thinking, they'll just divide 18.37 grams by 92.2 grams. So please be careful. A common trick that I do on a test is I'll put 18.37 grams divided by 92.2 grams and put that answer as answer A in the multiple choice section. Meanwhile, if you divided these two numbers, I'll put this answer all the way as option E. So if you're not careful and you're just rushing through things, you punch in these two numbers, divide them, you see option A has that exact answer, and you automatically choose A. So, now that I've told you this trick, it's not a trick anymore. If you fall for this on the test, you deserve it. Now, if you punch these values into the calculator, multiply by 100%, you should get 16.6% mm. And that matches up with the answer over here. So the remaining examples are more of the same. Again, watch out down here. The solution volume is equal to solute volume plus the solvent volume. So same trick over here, but instead of mass, I'm using volume. Please check your answers against the ones that are located here, and we'll just move ahead. One last thing though, make sure you remember that volume must be measured in milliliters and mass must be measured in grams. Now the next method of expressing concentration is through ppms and ppbs, so parts per million and parts per billion. The equation is almost identical to %mm. The only difference is instead of percent, so out of 100, we're doing per million, which means out of 1 million. So instead of multiplying by 100%, we're multiplying by 1 million. Same thing with the ppbs. Instead of the million in that case, we're multiplying by a billion. These two methods of expressing concentration are typically reserved for situations where you have a very dilute concentration. So for example, if my concentration was super low and I used %mm, I might have gotten something like 0.0000001%. So because the concentration is so low, a percent is not really great. It's not particularly useful because there's so many zeros. It's like trying to measure the speed of my car in meters per hour. I mean, if I'm driving down the street at 40,000 meters per hour, it sounds fast, but it's really only 40 kilometers per hour. So rather than dealing with super large numbers, it's much better to use the proper units. Well, it's the same over here. Using percent didn't really help you, so I probably want to try something like parts per billion. So instead of multiplying by 100%, I multiply it by a billion. In so doing, I can move the decimal place a few spots and get something like this, 0.01 ppbs, a much easier number to use than something long like this. Once again, make sure you measure the mass of the solute in grams and the mass of the solution in grams. And then depending on whether you want ppms or ppbs, multiply by 10 to the power 6, which is 1 million, or 10 to the power 9, which is 1 billion. So if you look at this example, symptoms of mercury poisoning become apparent after a person has accumulated more than 20 milligrams of mercury in the body. So express this amount as parts per million for a 60 kilogram person. So the 60 kilograms would be my solution mass. Don't forget to convert your kilograms into grams. So we multiply by 1,000, giving us 60,000 grams. And then we need to convert the 20 milligrams into grams as well. And in that case, we divide by 1,000 to get 0.020 grams. Now because we're asked for ppms, parts per million, we'll multiply that by 10 to the power 6, and that gives us 0.33 parts per million. If I want to calculate parts per billion, just change it to 10 to the power 9 instead, and we'll get 333 parts per billion. Now if we didn't use ppms or ppbs, and were forced to use percentages, we would change this and multiply by 100% instead, giving us 0.00033% mm, or if you want, 3.3 times 10 to the power negative 5% mm. Alright, so if the concentrations are very low, percent mm is not going to be helpful. The numbers are too small. It's probably best to use ppms or ppbs. Now the one thing that's missing from all these different ways of expressing concentration is the mole. For that we use something called molar concentration. Sometimes you'll hear it being called molarity, but we're not supposed to use this term anymore because too many people were getting it confused with the term molality, which expresses concentration in moles of solute per kilogram of solution. So let's just ignore these two terms, but be aware some of your teachers, myself included, may still use the term molarity because it's still being used quite a bit in industry. In any case, let's concentrate on molar concentration. So here's our equation. C represents the molar concentration, mole is the mole of solute, and V is the volume of the solution. Now be careful, the volume of the solution must be measured in liters. While %mv and %vv must use milliliters, molar concentration must be in liters, so don't forget to convert. Otherwise your answer will be off by a factor of 1,000. Alright, let's try this question out. How do we convert between %mv and molar concentration? So we're going to convert 27.5% mv of sodium chloride into a molar concentration value. Now if you recall, molar concentration, C, is equal to the mole of the solute divided by the volume of the solution. Unfortunately, we have neither the moles nor the volume right now, we just have a concentration. So the trick to this question is to assume a 1 liter sample. Now here's why I'm allowed to do that. Let's pretend I have a swimming pool and I filled it up with Sprite. Yes, Sprite. I then scoop out 5 liters of the Sprite and put it inside a bucket. Now if I drink from this bucket, will it taste less sweet than if I drank from the pool? More sweet than if I drank from the pool? Or the same level of sweetness if I drank from the pool? Disgusting, but the same. I haven't diluted the Sprite, I haven't concentrated the Sprite, it's the same level of sweetness. Well, what if I scoop out a 1 milliliter sample instead? Would this 1 milliliter of Sprite taste less sweet, more sweet, or same sweetness as this big giant swimming pool full of Sprite? Again, it should taste the same because I haven't done anything to it. I haven't diluted it, I haven't concentrated any further. It should be the same level of sweetness, whether I chose the 1 milliliter sample, a 5 liter sample, or a swimming pool sample. Well, same thing over here. If the concentration of sodium chloride in this solution is 27.5%, it doesn't matter if I have a 1 liter sample, a 10 liter sample, a 50,000 liter sample, it's still 27.5%. That won't change. Now, the only reason why I chose a 1 liter sample is because it will make my calculations a little easier later on. But you don't have to choose a 1 liter sample. You can put in your phone number here if you wanted to. It just makes the calculations a lot more difficult, that's all. So now that I assume a 1 liter sample, I can start plugging these values into my equation for %MV. Now just so you know, quite often we'll use this as a short form for saying solution. Since we'll be using this word quite a bit, you might as well start using short forms. Now while we're on the topic of short forms, here's a few more. Moles per liter can be written as a capital letter M. That's because the capital letter M stands for molarity. But because we're not supposed to use this word, we're not supposed to use this shortcut either. But if you look into my chemical storage room at my school, you'll find that many companies that sell these chemicals still use both methods to label their bottles. So if you're going to see them both in the real world, you might as well learn them both. Now another shortcut you'll see is if you see a square bracket around a chemical compound, that means concentration of. So in this case you would say concentration of H2SO4 is 5 moles per liter. Alright, so just putting a square bracket around it basically says that you are talking about its molar concentration. Now some students ask, how can you tell the difference between this square bracket in terms of concentration and this square bracket in terms of ions? Well, if you're using the square brackets for ions, the ionic charge is above and outside the bracket. If I wanted to talk about the concentration of the ion, I would put the charge and the symbol inside the bracket. Bracket, it's a lithium ion. Charge inside the bracket, we're talking about the lithium ion concentration. Alright, so these are the shortcuts we're going to use for now. Let's continue on with the question. So I'm going to start plugging in values where they belong, 27.5% MV, 1 liter solution goes in the volume, but be aware, when you're doing %MV, volume must be measured in milliliters. So we multiply the 1 liter by 1,000 and it gives me 1,000 milliliters. I can now punch this into a calculator and I'll get the mass of the sodium chloride is equal to 275 grams. Now that I have this mass, I can now turn it into a mole value. So mole sodium chloride is mass divided by molar mass 275, molar mass is 58.44, which we can get from the periodic table, giving me 4.705 moles. Since we assumed a 1 liter sample, I can just divide by 1, which of course makes my calculation easy, and I get 4.705 moles per liter as my molar concentration. But because we're dealing with 3 sig figs, this should actually be a 4.71. Alternatively, I can just write down 4.71 capital letter M instead of the moles per liter, and this of course is my sodium chloride molar concentration. Now, if you wanted to convert from molar concentration back into %MV, you would just do the reverse. But don't forget that you have to assume a 1 liter sample when you initially do this. Well, you don't have to assume a 1 liter sample. You can choose whatever sample you want. Just make sure you assume a certain sample. But once you choose that volume, you must use it here and here. Don't forget, %MV uses milliliters, while molar concentration uses liters. Now the last topic I want to talk about is dilutions. So making something less concentrated. Now, most of us know that juice can be sold in a can, frozen concentrated, but it can also be sold in a jug, ready to drink, and significantly more dilute than this. But what are the pros and cons of each method? Well, with concentrated juice, it's usually cheaper. Because it comes in a small can, you can store more of it in your fridge or freezer. And you can control how sweet it is by adding more water or less water to suit your tastes. But the cons for this is that it's not ready to drink right out of the can, not unless you want diabetes. So you have to supply your own water to dilute it with, and a container to hold it all. With the ready-to-drink jugs, however, you don't have to do any preparation and you can drink it right out of the jug. So it's a lot more convenient. The cons, however, is that it takes up a lot more space, it's usually more expensive, and you can't really make it any more sweeter than it already is. You can dilute it, make it less sweet, but going in the opposite direction and make it more concentrated, that's a lot more difficult. Well, these are the same pros and cons we have when deciding whether or not to buy a concentrated chemical from the manufacturer or a more dilute but ready to use concentration. But because money is always an issue, schools typically choose the more economical version. Now, a couple of key terms to keep in mind. A stock solution is a concentrated solution that will be diluted to a lower concentration for actual use. So for instance, at my school, we prefer to buy hydrochloric acid in 12 molar jugs. So that concentration is 12 moles per liter. However, we never let our students handle this because it is just too dangerous. So I must dilute it to a more reasonable concentration where I know my students will be safe, like 0.100 molar or 1.00 molar. Now, a standard solution is a solution of known concentration. Typically, it's used to determine the concentrations of other substances, like during a titration experiment, for instance. This is something we will talk about later on in this unit. But essentially, if you know the concentration of a solution, you can call it a standard solution. Or if something asks you to standardize a solution, it's telling you to find the concentration for that solution. Now, a volumetric flask is a piece of glassware that contains a very precise volume. These are often used in dilutions to prepare standard solutions because they're so precise. You'll notice that these volumetric flasks only have one line and one number on them, because they only measure one volume each, but they measure it super precisely. Alright, so let's walk through the process of dilution. We start off with a concentrated stock solution, typically purchased from the manufacturer, and we pour out a small amount of it. It's important to note that the concentration in this beaker right now is the same concentration as it was inside the stock solution. If you look at the yellow dots, they're just as crowded here as they are here. Now, all of the solute that will be inside my diluted solution comes from this step. Only some of the solvent that will be in my diluted solution comes from this step. I then add water to increase the volume of the solvent, and this begins the dilution process. You'll notice that the dots inside are now more spread out. They're not as crowded as they were here. When I reach my final volume, I have the same number of solute particles as I had here and here. So remember, all of the solute particles that I have in my final diluted solution comes from this first step. With additional solvent, these solute particles are now very spread out, so it has a lower concentration. We can see mathematically, same number of solute particles in the numerator, same number of solute particles in the numerator. But the solution volume is smaller here than it is here. Because you're dividing by a larger number, the concentration value will be smaller. So once again, none of the solute in my final solution comes from this step, but most of the solvent in my final solution comes from this step. Now, during these dilution calculations, you're only going to use one equation. C equals mole over V. But you're going to be using this equation several times. So I like to draw diagrams to help me visualize and separate these two equations in order to avoid using the wrong concentration or volume for each. Alright, so let's read over the problem and go through it together. Sulfuric acid is only sold in concentrations of 18 moles per liter. So from my stock bottle, I can label the sulfuric acid concentration as 18 moles per liter. Now, I don't want my students to burn their faces off, so I decide to dilute the acid to 0.10 moles per liter. So I'm going to label my final diluted sulfuric acid concentration as being 0.10 moles per liter. That's what I want. It then goes on to say that the class requires 2 liters of this diluted acid. So I'm going to write down V equals 2.0 liters. The question then asks what volume of concentrated acid and what volume of water are required to create the solution. So what volume of the concentrated acid needs to be poured in and what volume of water is required to dilute this. Now, as I mentioned before, we're only going to use the equation C equals mole over V, but we're going to do it twice. And that's why it's important to organize your information to keep these two sets of variables separate. Otherwise, I might mix up this concentration with this concentration, or this volume with this volume, or this volume, when they should be kept separate because they cannot be used together in one equation. So which side should I start off with? Over here, I only have one variable available, 18 moles per liter, that's my concentration. I don't have moles, I don't have volume, so I can't solve this equation yet. But over here, I have the concentration, 0.10 moles per liter, and I have the volume, 2.0 liters. So I can solve for the number of moles. When I rearrange this equation, I get mole is equal to C times V, where the concentration is 0.10 moles per liter, and remember moles per liter can be replaced with a capital letter M, they're both interchangeable, and the volume is 2 liters. When you multiply them together, you find that we need 0.20 moles of sulfuric acid in order to make the solution. Since the sulfuric acid doesn't come from my water, it must come from my stock solution. I know that I need to pour out 0.20 moles of sulfuric acid from here. But what volume is that? Is that 30 mils, 50 mils, 2 mils? How many milliliters of 18 molar sulfuric acid is required to give me 0.20 moles of sulfuric acid? Well, now that I have the mole value and I have the concentration, I can solve for V. So rearranging this equation, I get V equals mole over C. I know that I need 0.20 moles of sulfuric acid. That's what I calculated over here. And the concentration for this stock solution is 18 moles per liter. When I divide these two out, I can see the moles and moles cancel each other out, and I'm left with liters, which is volume. 0.0111 liters of sulfuric acid, 18 molar, will contain the 0.20 moles of sulfuric acid that I need in this solution. So now that I know what volume of the concentrated acid is inside my flask, I need to find out how much water I should pour in order to get my final concentration, because right now it's just the concentrated acid inside. And if it's just the concentrated acid inside, it's the same concentration until I add water to dilute it. Well, the question says I need 2 liters of this dilute solution. So when I fill it up, it should be 2 liters. So what volume of water needs to be added to fill it up from this line to this line? Well, by subtracting these two values, 2 liters minus 0.0111 liters, I get 1.99 liters. And this is the volume of water that needs to be added into my volumetric flask in order to create my diluted solution. And there's my answer. In order to create 2 liters of a 0.10 molar solution of sulfuric acid, I need to pour in 0.0111 liters of the concentrated stock solution and then dilute it with 1.99 liters of water. Now, when using a volumetric flask, you don't really need to calculate this last part over here. As mentioned before, volumetric flasks are very, very precise, very, very accurate, and calibrated to measure only that one volume. So if you filled it up to this line, that would be exactly 500 milliliters. If you filled this one up to the line over here, it'd be 250 milliliters. And if you filled up to this line, 100 milliliters. So rather than calculating the missing volume of water that needs to be placed inside, I would use a 2-liter volumetric flask, not a 500 ml one. And after pouring in my acid, I would fill it up the rest of the way with water up to the line. This not only saves me time in having to calculate what volume is required, and also having to measure out 100 milliliters of water, then pouring it in, then refilling with 100 ml of water, then pouring it in, over and over and over again until I got 1.99 liters. Keep in mind that these graduated cylinders are only accurate to plus or minus 1 milliliter. So each time you poured in 100 milliliters, you're introducing an error of plus or minus 1 milliliter. Maybe you're only pouring 99 milliliters or only pouring 101 milliliters. It won't be exact if you do it 19 or 20 times. You can avoid all of this by just using a volumetric flask and filling it up to the line, because this is very well calibrated, it is precise, it is accurate. And that is the general layout on how to do a dilution calculation. Like I said, I like to organize these calculations. Don't go and draw nice pretty pictures, that's a waste of time. Just draw a little box to represent each of these. But again, remember that all of your solute comes from this step. None of the solute comes from here. While some of the volume comes from here, most of the volume comes from here. So some of the volume comes from here, but most of the volume comes from here. Alright, so here are some practice questions for you to play with. Make sure you're doing them properly and check your answers against these. But let's try question 6 together. So, I have a 350 milliliter, 65% NV saltwater solution. So I'm just going to draw a little picture. Here's what it currently is, 350 milliliters, 65% MV. What I want to do is dilute this solution until it becomes 40% MV. So I want to add water until it becomes 40% MV, so less diluted than it is right now. So the question is, what volume of water must be added to do this? All right, so how much do I need to fill it up? So the first step is to write out the equations. Now, instead of using C equals mole over V, we'll be using the percent MV equation instead. But just like in the last question, we'll be using that same equation twice. So it's important that you keep things separate and organized so you don't mix up the variables. Now, which side should I start off with first? Over here, I only have concentration. I don't have the mass of the solute. I don't have the volume of the solution. But over here, I have the volume of the solution. I have the concentration. I can solve for the mass of the solute. So I'm going to substitute the values in. And because it's percent MV, I can leave the volume in milliliters, which is what I'll do over here. Now let's solve for the mass of the solute. Rearranging the equation, I can multiply out the 350 and divide out the 100%, giving me 227.5 grams of solute. Now, since I'm only adding water on this side, my solute comes from this side only. So whatever salt was present on this side is also present on this side. I'm not adding more salt, I'm not removing salt, so it's the same mass of salt. So now I have the concentration for this equation and the mass of solute for this equation. This allows me to solve for the volume of solution. So substituting the values in, I can rearrange the equation so that the volume of solution is equal to the mass of solute divided by the percent MV times 100%, giving me 568.75 milliliters as my new solution volume. So if the old solution volume was 350 milliliters and the new solution volume is 568.75, I can subtract these two numbers, giving me 218.75 milliliters of water required to add to the original solution in order to make it a 40% MV dilution. I then confirm it with my answer key and we're good to go. Alright, so that is our lesson on dilutions.